I will, as was said, talk about how much more bandwidth do we need for wireless communications, which will turn out to be a question that is much more broadly and maybe complicated to answer than it at first seems. But I hope to walk you through some of these things here in the coming 40 minutes. So one of the important things that forces us to change wireless communication networks all the time is this exponential traffic growth. And there are different companies, for example Ericsson, that are measuring these things, and what they're seeing is that the data traffic is growing rapidly, both back in time but also predicted to do that in the future. So it's typically 30-40% per year that it's the increase, and the voice traffic is not increasing very much because people are communicating in other ways these days. But it really means that even if you have a network that works well today, then just wait a few years and the traffic will have grown so much that we need to build it in a different manner. And the obvious answer perhaps would be that, okay, you have more traffic, we need more bandwidth. But what does it really mean to have more bandwidth? Because if you start to look around and ask people, bandwidth actually has two dominant definitions. So what does bandwidth really mean in communications? Well, if you ask an electrical engineer, they might say that this is the width of the frequency spectrum that you use for signal transmission, and you measure it in hertz. Then you talk to someone in computer science and say, no, this is the amount of data that you transfer per second, measured in bits per second, which is apparently two different things. And the connection between these two things is coming from the Shannon-Hartley formula, or sometimes we call it just the channel capacity. So the bit rate, measured in bit per second, is equal to the product of two different things. There is the spectral bandwidth, the thing that electrical engineers are talking about, and the reason that this enters in here is due to the sampling theorem that says that we can sample a signal at a certain rate, namely proportional to the bandwidth, and that is the number of digital symbols that we transmit per second. The second thing is the spectral efficiency in bits per second and hertz, and this is determined by the modulation format. So how many digital bits do we squeeze into each symbol that we transfer over our channel? And if you multiply these two things together, you get something in bits per second, so that is the bit rate. So when people in computer science talk about bandwidth, they are treating it as the same thing as a bit rate. And there are good reason for this, because in wired communication, which is what computer science is normally based on, you have a fiber cable, for example, spectral efficiency is fixed. You have a cable of a certain kind, and therefore the spectral efficiency is predetermined, and then bandwidth and bit rate becomes proportional to each other. So you can, of course, treat them as being the same thing. But as soon as you move into wireless communication, this is not a good practice anymore, because the spectral efficiency is varying immensely depending on where the user is and what kind of equipment they're having and things like that. So this large variation in spectral efficiency means that for a given bandwidth you can get vastly different bit rates, and therefore we need to treat this in different ways. So when I am talking today about bandwidth, I will mainly use the term bandwidth as the spectral bandwidth, but bitrate will be equally important throughout this presentation as well. So to connect this a little bit further, depending on your background, of course you send information between the base station and a mobile phone or back again, and then you are representing your data with zeros and ones, and you take your data sequence, you chop it up into different small segments, and you represent, in this case, 2 bits with one waveform. So 0, 0 by the red one, 1, 0 with the blue one, 1, 1 with the purple one, and 0, 1 with the green one. And then you repeat it like that every time you are transmitting. And the challenge in wireless then at the physical layer is really that you transmit this, but what you receive is a highly attenuated version where you also have added noise to it. So you receive something like this, there is no coloring or anything, and you need to create your communication algorithm that can make sure that you output the sequence which is matching with what you were transmitting. And then going back to the previous slide, the symbol period here is 1 over the bandwidth, and this is then you're transmitting the bandwidth number of symbols per second. And the spectral efficiency, that is the number of zeros and ones that we are representing using each of the symbols here. So in this case it was 2. And how many can we transmit? Well, if we go back to Shannon again, then the bit rate is equal to the bandwidth times the spectral efficiency, which has this formula. So there is a log 2 or 1 plus the received signal power divided with the bandwidth times n naught, and this is the noise power spectral density. So that is given by nature. So you see, bandwidth are appearing in 2 places, the received signal power, and when you compute this number here, which is the spectral efficiency, well, then you might get a number, which is 2, and then you should send exactly 2 bits. And if you get 3, you should have more different waveforms that represents up to 3 bits. And you can have something in between 2 and 3 by using, for example, channel codes. So not every bit here is actually information bit. Some of them are parity bits. Okay, and the reason then that we get these large variations in spectral efficiency in wireless is due to the wireless propagation. And there are these 3 main categories of issues. One of them is just the geometric path loss. So if you put out the base station at a certain location, you measure the signal strength at different locations here. I have a 500 by 500 meter area, and I've used at different locations and I measure what signal strength they will get. Then because the signal is spreading out over a bigger area, the signal becomes weaker and weaker, and that makes the spectral efficiency drop. So if you have, say, 8 bits per second per hertz, the biggest you can get in Wi-Fi, for example, in the center of the cell, well, then it starts to go down, and at the edges of the cell you have much smaller numbers. In addition to this, if you zoom into a small region here, you will also see what we call small scale fading, small rapid variations. So these rapid variations could be just in a 1 meter by 1 meter area. When the wavelength is 0.1 meter, which is 3 gigahertz band, then you just move a fraction, say a quarter of a wavelength, and then you can get from a peak value to some value that is 1/10 of the B smaller. So you have these small variations. Why? Well, because the signals are not only coming directly from the base station, they are bouncing on different objects, and that is creating these rapid variations through coherent and destructive interference. And finally, if you don't see the base station, you have what we call shadow fading, so the signal needs to propagate through different objects, and then you have immense losses from that as well. So all these 3 physical issues are creating the fact that we can't rely on that we get the same spectral efficiency everywhere for every user. It varies immensely between where users are. So if you just want to create a simple model of this, well, here is one from the 3GPP that they are using to measure quality in standardization. So it's called the urban microcell for non-line of sight scenarios for the 3.5 gigahertz band. And they're saying that the gain of the channel, so the thing you should take your transmitted power and multiply with in order to get your received power, there is a constant, and then you divide with the distance to a certain exponent, which in non-line of sight scenarios is a larger exponent than 2, while its line of sight is 2. You can see that this channel gain is rather small, and already at short distance, a few tenths of meters, it is minus 70 dB, and then it starts to go down even more as you move up in distance. And what this turns into is that if you now put this kind of behaviors into your capacity formula to compute the spectral efficiency, you have log 2 or 1 plus, bandwidth and n naught is the same, but the received signal power will be the transmitted power multiplied with this channel gain. And since this one is going down, we get the same kind of trend here, that depending on the distance, you get a smaller and smaller spectral efficiency, and therefore you get a smaller and smaller bit rate. And typically there are some maximum spectral efficiency that your hardware can support. For example, it might be 10, and when you are then at different ranges beyond, say 100 meters or so, we are limited by the signal strength instead. And yeah, there are some assumptions behind these things here in order to do the computations, but the same trends will appear irrespective of what kind of assumptions you are making, how much bandwidth you have, or what transmit power you have, or what are the antenna gains. This is the general trends. Okay, so what if we add more bandwidth, spectral bandwidth, and we start from one particular point? I take from the previous slide, I'm at 600 meters away, and I'm starting from having 10 megahertz of bandwidth, which is what you typically had in a 4G system, or at least you're down somewhere over here. Then, if everything else is fixed and I just add more bandwidth into my system, if I increase the bandwidth by 10 times from 10 megahertz up to 100 megahertz, this is what we typically have in 5G today, then you would expect, okay, I multiply with the bandwidth in front of the spectral efficiency, so I should get 10 times more bitrate. But you don't. You get only 4 times. And why is that? Well, actually, the capacity formula was the bandwidth times log 2 or 1 plus received signal power divided with the bandwidth again times n naught. Because we take our transmitted power and we spread it out over a larger and larger bandwidth, and therefore we get some losses in signal strength per hertz as well. And if you then continue and increase the bandwidth with another 10 times, from 100 megahertz up to 1000, so 1 gigahertz, well, it turns out that you have even more diminishing returns. So then you only get 2 times. And then eventually, when you let the bandwidth increase even more, you converge into an upper limit, and you can show mathematically that when the bandwidth goes to infinity, there is a certain upper limit here. So just adding more bandwidth into our system will eventually have this diminishing return, and it will not be worth trying to get a license for having more bandwidth than a certain number. So just for simplicity, say that when you reach 80% of this upper bound, it doesn't pay off to get more bandwidth anymore. Well, in that case, in this scenario, this will happen when you are at 2, 3, 4, 500 megahertz. And depending on your propagation distance, this will happen at different locations. So here is another way of looking at this. So I have the propagation distance here, and then I'm showing with this red line here for what bandwidth value do you reach 80% of this bound. So at 600, we are at this point here, so 500 megahertz. If you are at further away distances, well then you already today have enough bandwidth in our system to reach the upper bound. And if you are at shorter distances, you can still benefit from more bandwidth. But the main point here is that for a given setup with a certain channel gain, there is a maximum really useful bandwidth in our system. And we are approaching those things not either now in 5G or in the near future, at least at longer distances. There is certainly a way of pushing up the upper limit. So the upper limit was here the received signal power divided by n naught, and then there is a factor here. And if we can increase the received signal power, well then we can also push the limit upwards, and therefore we can benefit from having more bandwidth. And there are 3 different main ways of doing this. One would be to amplify your signals more strongly. So you transmit with the higher power, and when the power then is reaching the receiver, it will be stronger just because the transmit power was stronger. Typically, this is hard to do because you have regulations on how much transmit power you have. You need to use the device to be able to reach you back, and the user device is powered by a battery. And there are other reasons, like it's when you go up in bandwidth, it's often harder to build good amplifiers, for example. Another alternative would be to make the receiver larger. And then it would capture a larger fraction of the electromagnetic waves, and therefore we receive more. This is typically not what you're seeing as a trend, but you rather see how devices become smaller and smaller. And at least at most that the antenna sizes are staying the same inside devices. The third option would be to direct the signals more clearly towards where the users are, so you transmit in a directed manner. And this is what 5G to a large extent is about. Okay, so to go back and rephrase the original question, it might not be bandwidth as such that is the important thing, but bitrate. So how much higher bitrates do we need? Because we had this trend here, the demand for data is increasing with 30 to 40% per year. So what do you need as a user? Why is it increasing? Well, if you look at some of the potential applications, like video streaming, if you are having full HD quality, you need 5 to 10 megabit per second. If you have a 4K video streaming, so ultra high definition, maybe you need 20 to 25 megabit per second. Online gaming, not that much. Maybe if you look into the future and you think, oh, people will walk around with some virtual reality glasses that is covering the 360 degrees of your view, and it's 3D and all kind of things. People have some different expectation of what that could be. Maybe 50 to 200 megabits. Some people say up to 1 gigabit or a few gigabits. But the main point is that we can easily deliver this today. 4G supports up to 1 gigabit per second, 5G supports up to 20 gigabit per second. The problem are actually two when it comes to achieving this. One is that the data traffic is mainly increasing because it is the accumulated traffic that is growing. It's not like you, when you use your device, will next year require a 40% faster speed for your applications, because these are still the most data demanding application you're using. No, it's rather that you are using your device more frequently, and you are also having many more devices. So it's the accumulation of data traffic for many devices that is really growing, not the demand per device. And of course, we also had this issue that even if you can, in best case scenarios, achieve very high bit rates, which are far beyond what you as a user need today, well, we don't get that all of the time. So if we are mainly interested in handling traffic that is growing, not on a per user basis, but because of the accumulated traffic is growing, bandwidth isn't the only thing we can play with. Actually, the traffic capacity of a network in bits per second per a certain base station or a certain cell of a cellular network, there's 3 different factors that we can play with. The first one is certainly the bandwidth in hertz. The last one is the spectral efficiency, bits per second per hertz per user. And the last one is the number of spatial layers, the number of transmissions that you have simultaneously with different spatial directivity. And this is then proportional to the number of users that we are serving, for example. So other ways of viewing this is that if you in 4G network had this kind of situation where you have a base station site, it has directive antennas that are covering a particular sector, and within that sector we can only serve one user at a time. Then with 5G, we have what we call massive MIMO. We have these antenna arrays with, say, 64 antennas that are connected to their own radius, and we can therefore control what kind of constructive interference that they are creating with the transmissions, resulting in that we can send beams towards users in different directions at the same time. So these networks are not necessarily increasing the spectral efficiency at all, but they are adding more spatial layers because you can serve more use at the same time. And this is really then done to cater for having more traffic created by more users, and not because of the demand per user being increasing. And I think there is something interesting happening here that you can create an analogy with when it comes to computers. So the green curve here is showing over time how with high performance computing, the clock frequency have been increasing over time. And being someone who started working with computers in the 90s when I was growing up, well then I was remembering that around year 2000 we hit 1 gigahertz as the sampling rate, the clock frequency. And beyond that you were expecting, it would just continue increasing, but that didn't really happen. If you buy a computer today, you just have a few gigahertz as your clock frequency. What has instead happened is that it of course improves our circuitry, but also that around year 2010 the number of cores that you have in your computers is increasing instead, while the clock frequency is not increasing. And you're then creating something that's more powerful because you are doing multi-thread computing. And the past then was that we are making things more efficient by having high clock frequency, and the future is that we have more cores and multi-thread computing. And the same thing is now happening, I believe, with wireless. The past was that the way of getting higher speeds was to add more bandwidth. So you get a higher sampling rate, so you can transmit more symbols per second through our wireless channel. But that turns out to then not be a very useful approach in the future because of this diminishing returns from adding more bandwidth. And then the alternative would be multiple cores, which means in our case, multiple layers, multiple spatial transmissions that are happening at the same time. And this massive change is happening now. It happened for computing some 10 years ago, and now it's happening in wireless communication. So this is an example of a 4G type of passive antenna. It is vertically tall, but not very wide horizontally, so it creates a broad directivity horizontally but narrow vertically, so you keep the signal down to earth where people are. And what we are now using in 5G is this kind of massive MIMO panels. So they are typically designed for the 3.5 gigahertz band. This particular one that I'm carrying is 32 antennas inside of it, so with radios and everything, weighs 12 kilos, and you can use it over 200 megahertz. There's integrated circuits that is doing all the kind of physical layer computations that you need, at least part of them. You can also buy some of this equipment behind me there, which are 64 antennas. And this is what's really used. I was talking with people at Huawei the other week who were saying that just in China, there is 2 million base stations of this kind, of course produced by Huawei then and not Ericsson. But this is all around us now. And this is what we call massive MIMO, and it has the capability of sending beams in different directions. So what we are really interested in moving into the future is to get more traffic capacity. And we can achieve this in different frequency bands. People are often talking about that, well, we need to go up a millimeter wave to find more bandwidth. And that is true, but that doesn't mean that we need to do it in order to handle more traffic. So if I will distinguish between 3 different cases here, the low bands that we're traditionally using, where we have a limited amount of bandwidth, but we have a good coverage, the mid band, where 5G is deployed these days, and the millimeter wave bands going beyond, say, 7 gigahertz, and this is where you have a large amount of bandwidth, but rather poor coverage because the wave propagation is not as useful. So it's more for short ranges. Then, let me give you some examples. So, say that you start in the low band. You have 20 megahertz of spectrum in the 700 megahertz band. And that this could allow you to achieve 200 megabit per second. Well, then if you go up to 5G, we typically have, say, 5 times this. So 5 times higher carrier frequency, 5 times more spectrum, and that is then turning into 5 times higher bitrate per user, if we can sustain the same SNR. If you move up to millimeter wave, well, one of the millimeter wave bands is 35 gigahertz. So let's take that because it's just 10 times larger. And there you might be able to find 10 times more bandwidth, and therefore you will get 10 times higher bitrate per user. But now comes the interesting thing, that when you are building these networks, you need to learn the channels, so you know where to point your beam, and that you know you can transmit so the receiver can coherently receive the signals. And the limiting factor there is how quickly the channel is changing, and that is inversely proportional to the wavelength. So if you go up in frequency, the wavelength gets shorter and you move a fraction of wavelengths more rapidly, and then you get these rapid variations due to small scale fading. So if there is a certain number of spatial layers, X, that you can serve in the low band, and this is limited then by mobility, then when you go up in frequency by 5 times, the wavelength shrinks by 5, and you therefore can only afford to learn the channel for a fifth of that number of users. And you go up 10 times again in frequency, and you reach the millimeter wave bands, and then you need to divide by 10 here, so you get fewer and fewer spatial layers that you can serve in the best cases. So in all of these cases here, it's like 200 times X. This is going to be the number of megabit per second that you can serve. So if you get more per user, you get fewer users. That is essentially the game we are playing here. So all of these different bands have solutions to handle more traffic. So it's not all about bandwidth. So if we look beyond bandwidth, if we say, okay, we would need to live with the bandwidth that we have today, what can we do? Well, there are 2 possible future developments that I am foreseeing in particular. The first thing is what we call cell-free massive MIMO. This is based on the idea that instead of having these tall towers with a lot of antennas inside a box, then you take the antennas apart and you spread them out over the environment. The idea would then be that instead of having tall towers surrounded by users, every user will be surrounded by low power transmitters all around them. Wherever you are here, you are surrounded by access points. And there are 2 main benefits of this. The first thing is that you have a shorter distance to the access point most of the time. So these rapid variations, or the geometric path loss I described when I was showing that when you are in the center of the cell, you get a good signal, and if you are far away, well, the signal goes down. Then this is not happening as rapidly here because you are always close to some of the transmitters. The main challenge, though, is that when you're close to many transmitters, they will interfere with each other. unless you let these devices collaborate. And that is what cell-free massive MIMO is doing, and I will have 2 more slides talking about the details around that. The other option is to go from having massive MIMO base stations, which are called massive because they contain many antennas. They are massive in numbers, but they are not physically large. If you put them at the cell tower, well, they might even look smaller than the base station that you had in the past. So when they are transmitted to the user, well, they are creating these kind of directive signals towards the user, like a flashlight, but that's it. You can use it to multiplex multiple users, for example. But when the traffic is growing, we can potentially build even larger antenna arrays that we will have to deploy in different ways, like spreading out the antennas along the side of the building here. We will call this extremely large aperture arrays because, yeah, the aperture, the size of this is really large compared to the wavelength. And why would you like to do this? Well, first of all, you can serve many more users because the larger the array is, the more you can focus a signal into small regions. So here is an illustration of that, where you're focusing just at the region around the user. And you also enter into new propagation scenarios, go from being in the far field to the radiative near field, where signals focused at the user doesn't lead to a beam like this. They are leading rather to that we are focusing the signal energy just in the small area around the user. And this might also allow you to send multiple layers per device, even in line of sight scenarios. So I will spend a little bit of time on digging into the details of these 2 different technologies. So cell-free massive MIMO is really an architecture that is designed for the worst case scenarios because of this thing I was talking about before, that the bit rate that you need as a user isn't really increasing very rapidly. You will do your video streaming, and as long as you get some 20-30 megabit per second, you will be satisfied with that. But the problem is that you don't have a coverage everywhere that is giving you that kind of bit rates. So that's why you are sometimes having the trouble that the network is not fast enough for you. And here I'm illustrating first 2 different ways of building networks of today. You can have big cells, say 100 antennas on each cell tower, but only a few of these cells. Or you can take the same 4 times 100, so 400 antennas, you spread them out into 400 cells. I put them on a square grid here. And then as a user, I'm walking around here and I'm measuring what signal I'm getting at different places. What is my spectral efficiency? And this is what I'm showing here, spectral efficiency on the horizontal axis and a cumulative distribution function, so describing the randomness that I'm seeing when I'm moving around. And there are 2 curves, one for the case that I call cellular massive MIMO, big base stations at a few locations, and one with what I call small cells, 1 antenna per cell spread out, there are many of them. The 2 curves are roughly the same. And this is what is interesting because for a user, it doesn't really matter what your operator decides to transmit or deploy here. The transmission to you will be roughly the same in terms of your quality. Sometimes it's good because you're close to a base station, either to one tall one or to a small one. And sometimes it's bad, and that is either because you have big cells and at the edge of the cell you have weak signal, or because you have small cells but you are at the edge between cells where the different access points are interfering with each other. And in both cases you get bad performance. So how do we resolve that? Well, you want to have small cells so the signal is strong, and then you need to deal with interference. And this is what cell-free massive MIMO is about. So you let this access point collaborate so that they are transmitting to you from different directions. They are phase coherently transmitting, so that the signal comes from a different direction and they add on top of each other where you are. And at the same time, you can deal with interference elsewhere. And all of the mathematical details, you can find it in my book, Foundation of User-Centric Cell-Free Massive MIMO, which you can download for free online. I will just continue showing you this kind of graph here. This is actually one of the simulations that is in the book, and we are getting a curve for what is the variation you get as a user. Well, in the bad cases from before, you see a big gain. And in the good cases, well, you don't see any big gains because you are already close to 100 access point, and that will be the one that serves you most of the time. There are certainly practical issues with trying to build something like this, and this is something that we have been facing when we are talking with industry about this. And one is that you might create what we call a spaghetti monster. So say that you have some places where you are facilitating your collaboration, some processing units. And then at the edge of each noodle here, you have an access point. And between them, you need to have a cable. And that just becomes a lot of cables, as here, a lot of noodles. So this is what it really looks like then. You have your processing unit, some edge computer somewhere, you connect all of your access point to them through cables, and it just becomes a lot of cables. So even if you can build this, no one is building it because of the sheer amount of cables. It's just too complicated to build. But one of the potential solutions to this is that these cables here, which we call frontal because they are between the processing unit and the access point, we could make it sequential. Meaning that if you have a number of access points, you can let the cable go between them. And in particular, you can view it like, I have my processing unit here, I have my access point up here, I would need to put a cable between them. Let's then put additional access point along this cable. And then you reduce the amount of cables, and you might be able to do this more practically. And we have this implementation concept that we developed some time ago when I was working at Linköping University together with people at Ericsson, because we were really saying, look, here are these great benefits that a cell-free massive MIMO, distributed MIMO scenario could have. And they were saying, well, yes, we recognize this, but we will not be able to deploy this or let any operators actually buy it because they don't want to have that much cables. So the idea here is really to have a processing unit, you have a cable, fiber cable for example, that you are dragging until the furthest away point, and then along this cable you put some antenna units that can create radio frequency signals, and then you are connecting them to physical antennas that send the signals. And depending on the carrier frequency, the antennas might be larger than the cable. So if you think about this like a fiber cable or an Ethernet cable as a thickness, well then if you are in the 3.5 GHz band, the antennas will be larger, so you need to stick out, as I'm illustrating here. But when you go up in frequency, the antenna processing units here might be comparable in size to the antennas, so you can probably just put the antennas on top of them as you go up in frequency and potentially have multiple of these antennas within the same processing unit. So this is a concept that Ericsson calls radio stripes. They were showing it at the Mobile World Congress at 2019 just as a concept. These are just printed plastic. But the idea is that you eventually should be able to build this with printed electronics, and this should enable us to deploy networks in this new way so we can handle more traffic, but in particular deal with interference so you get a more consistent performance as a user. The second direction that I mentioned was this extremely large aperture arrays, which is to some extent about utilizing the depth domain. So before, you're transmitting from your base station, you're creating these angular beams towards the users, and then when you have a particularly large array where you are in the near field, you are more focusing the signals. So you can think about this like if you're taking photos with a camera, if you're taking the photo focus on someone who is far away, well then you get a depth that is going towards infinity, so it's sharp at the person and behind them. While if you're taking a photo at someone who is nearby, you get a blurry image behind them. And that is the same kind of effect here when you're transmitting a signal towards the user. You get a signal that's only focused in a small area around where the user is. And there are some mathematics behind this, which is essentially saying that if you put up a big array here, then the area, the aperture area, is very important. If you take that area and you divide it with the wavelength squared, so you essentially say how many small pieces of that is wavelength times wavelength do you have, and then you multiply this with pi, then you get the number of resolvable signals that an array like this can handle. So to give you an example, say that it's 10 meters long and 30 meters tall. So this is a building. In the 3 GHz band, so the wavelength is 0.1 meter. Well, then you do the math here and you see you get 100,000 if you would fill this entire facade here with antennas. And of course, you can get smaller numbers by not actually having antennas everywhere. So this is really saying that you can, if you put out antennas over a big surface, serve immense amount of users. So for example, you can increase the array sizes as the traffic is growing. So when you have more traffic because you have more users, you make the array surface proportionally larger. So when your traffic is doubling, you double the array area. And yeah, in that way you will just be able to resolve that number of signals. Some of the practical issues here is, of course, to build this in a good way, and that the complexity increases a lot, because the complexity of doing some of this transmission is typically proportional to the number of antennas times number of users squared. The squaring comes from that you are trying to control interference between them, so you get some kind of matrix inverses there. You might be familiar with zero forcing, for example, as such a method. So the complexity is growing here cubically with the number of users if you increase the antenna area proportional to the number of users. So these are some of the issues here, certainly. But what are the opportunities? Well, in addition to just serving more users, you get this interesting new phenomena that allows you to serve users in a much better way. So traditionally, you have an antenna here, you have a user here, you focus a signal at the user, you are in line of sight scenarios, and then when you're transmitting this beam, the beam starts in the far field and then it propagates towards infinity, and around the user it will be very wide. And that's why you can only transmit one signal at a time to this user, because the user can only resolve one signal coming directly from the transmitter. But when you are in the so-called radiative near field, then you get these focusing things, the finite depth that described. So if you move the user close by and you refocus towards that user, well, you get a strong signal around the user, and then behind the user, the beam just starts to disappear, just as the focusing is doing when you are taking a photo portrait of someone who's nearby. And that allows you to simultaneously serve someone else who is in the same direction, but at a different depth. And you can continue doing this for multiple users. So multiplexing of use in the depth domain is one of the things that these big array surfaces are able to do. And as an alternative, if you're focusing at a user that is nearby, well, then the beam will be so narrow that you can actually send multiple beams towards different parts of the device, even in line of sight scenarios. And that allows you to transmit multiple signals to the same user at the same time. Of course, if you have objects around here, you will also get additional signals that are bouncing on them, and that might also increase the rank of your channel. The main thing here is that mathematically, you can just take your knowledge about how MIMO communication with multiple antennas at the transmitter and receiver is already working. It's the same kind of math. It's just that the channel matrices needs to be modeled very differently, because we get this new phenomena that start to dominate, and therefore we get new performance, even if the theory is the same. So to give you one final example of this, so here is I'm showing a scenario with 4x4 MIMO. So I have 4 transmit antennas here, I have 4 receive antennas here, and then I am putting them out with a certain distance that is determined by some theory, so that I can make sure that the channel from my 4 antennas to my 4 receive antennas here, even in line of sight scenarios, gives you 4 resolvable directions that are equally strong, more or less. So the strongest one is 26% of the received signal energy is arriving there. The second one also 26, the next 25, and the last 23rd. So they're roughly the same. And this means that over this type of channel, you can transmit 4 times as much data as you will be able to do with the same signal strength, but when you are in the far field. And the way you are transmitting is what I'm illustrating here with the coloring. So the yellow here is what you are getting at the focal point. So the strongest beamforming gain, the focusing. And you see that we are never focusing the signals exactly on the receive antennas. We are focusing on other points, so we get a pattern that becomes resolvable. So it's more like this green colors where you get part of your beamforming gain. That is what you see around the receive antennas. But by transmitting in this way, you can communicate even more data over your channels, and this is what really matters, not if the signal happen to have a beam shape or not. So 4 times higher capacity here. So finally then, to wrap up, what are the developments that we are seeing over time? Well, in 4G, what we typically were doing was to operate in the sub 6 GHz frequency range and using passive antennas which have a particular directivity, but they are fixed. And in 5G, we have expanded the range of things we can build. We can still build the same kind of thing, but we are focusing more on to go up in frequency to millimeter wave bands, where we can expand the bandwidth from being 10, 20 up to 100 megahertz up to 1 gigahertz perhaps. But we're also going up to massive MIMO, where we can serve, what you see on the vertical axis here is the number of spatial layers. We can serve maybe 10 users at the same time. And here we have the bandwidth dimension. So we have this range of things. And so far, the dominant thing that has been deployed is massive MIMO in the lower frequency bands, or what we call the midband. Nevertheless, since millimeter wave was a big fuss, there has been a lot of talk about that beyond 5G systems will go up to even higher frequencies to get even more bandwidth. And we will certainly develop that type of technology, but I think it is in very few occasions that you really need it, because you don't really have more useful bandwidth except at very short distances. So what I believe will be the major thing in the future is that we will continue building larger and larger MIMO systems and operate in the same frequencies as before, sometimes use millimeter waves as well, but in particular focus on these new dimensions, increase the number of spatial layers instead of increasing the bandwidth. And the conclusion then is that we need higher accumulated bit rates, not necessarily bandwidth, because the useful bandwidth per user is between a few hundred megahertz up to a few gigahertz, and it depends on channel gain. It is number of spatial layers that matters, and we can achieve more layers in several ways. We can have this physically large aperture arrays, or we can have the cell-free massive MIMO scenarios with the antennas being spread out. So if you are keen on knowing more about these two different directions, I have several YouTube videos that you can watch, both focused on cell-free massive MIMO entirely and on these physically larger arrays in particular that you can find on YouTube. And we also talk about this in my podcast, Wireless Future. So thank you very much for listening.